Hey guys, how's everyone doing today? Doing pretty good myself. Good to hear. Alrighty. Okay. So today we're going to finish up talking about surface integrals of vector fields. Okay. So we saw last time that if we think of if F is a field, a vector field, we can think of it like a force field, or also like a velocity field of like a fluid or something. So like at each point, you look at the particle of fluid there and look at the velocity vector of that fluid, and that is the vector field of that particle of fluid. So if we have some surface, say some beautiful surface S, and we have a vector field. Think of it as velocity vector field, perhaps. We can look at the rate of flow of fluid across this surface. So suppose that's our vector field, and it's flowing across our surface. So we can look at the rate of flow. Let me say the flux of your vector field F across S is the rate of flow of F across S. So we want to keep track of what direction we're flowing across S. And so we need to give an orientation of S. And we do that by at each point picking a positive unit normal vector. So at each point, we pick a positive unit normal vector n on our surface. And essentially that's essentially going to be like picking a side of our surface. So all the surfaces we deal with, and probably all the surfaces you can think of off the top of your head, have two sides, right? You think of a table, there's a top side and the bottom side. If we were to pick a positive unit normal vector, at each point, that would be picking either the one that points upwards, because that is going to be normal to the table, or the one that points directly downwards, which is also going to be normal to the table. So that's the same process we do with the surface. Either we pick all the ones that point towards one direction, or all of them that point towards the other direction. And that's essentially going to determine the positive direction of flow across our surface, right? So if this is our vector field here on our surface, oops. If we decide this is our positive normal vector, well, technically we pick a point at every single side. So it'd be something like this. Then the the vector field would be flowing across our surface in the positive direction, and the flux would be positive. If instead we chose the opposite, beautiful. That ain't it. All right. If instead we chose the opposite direction to be the positive unit normal vector, why do you do this? Then the one pointing downwards in this case, then we'd be the flux would be negative. The fluid would be flowing across, not in the positive direction. Okay. So we said, so what we do is we look at the vector field at each point, and we take the dot product with the positive unit normal vector in. And that gives us the normal component of the vector field. So if you remember back to projections way back when we projected one vector onto another, F dot n is essentially projecting the vector field at each point onto the normal vector. And that tells us the bit of the vector field that's pointing in the direction of the positive unit normal, or is parallel. It could be pointing in the opposite direction. And so that's the thing we're going to be integrating over the entire surface. So the flux of a vector field F across the surface S is the integral over the surface S of F dot n with respect to surface area. So we integrate the normal component of the vector field over our surface with respect to surface area. And we say that's the flux of F across S. You could also say the integral of F, the vector field F. If we're not considering F to be a vector field or anything physical of that nature. Anything physical, just a normal vector field. So we could just integrate a vector field over a surface and not consider anything physical. We wouldn't say the flux, but you could still say the flux in that case. But yeah, those are just two different terms that mean the same thing. Okay, so once again, if we want to evaluate this, well, we already went through this. I don't want to hash this out again and waste too much time on it. But another way of writing this is the integral over the surface S of f dot d vector s. And we think of d vector s as the positive unit normal vector times ds. This is probably the way we see it written more often. So that's the integral of f across s, vector field f, or you could say the flux of f. Okay, so let me do this on another page. Okay, so our unit normal vector so we can think of it as what I will write as, this is a little different than what I wrote yesterday. It's going to essentially be the same thing, but it's going to be maybe a little less ambiguous. So it's going to be capital N of uv over the magnitude of n of uv. And so capital N is going to be the cross product. Remember, if we parameterize our surface by g of uv, it's going to be the cross product of g sub u cross g sub v or g sub v cross g sub u, depending on orientation. Right, so we need to give our surface an orientation. And so here's our surface. So at each point, you have two choices for positive unit norm for the positive unit normal vector, little n. So there are two vectors which are magnitude 1, so it's a unit vector, which are normal to your surface, so orthogonal to the tangent plane. So the one pointing and one that's one, so there's one vector that's tangent to it, and then there's one pointing in the opposite direction. One of those is going to correspond to GU cross GV over the magnitude GU cross GV. The other one is going to correspond to negative of that, or you could flip the cross product. And we need to figure out which one of those. In other words, we're going to determine like the positive side, the positive direction of flow across our surface. Choosing one of those at each point is how we do that. And so suppose this was our surface. I could say we choose the upward pointing orientation of the surface, or the positive unit normal points upwards. So in this case, we would say all our positive normals point in this direction, upwards. And then we'd figure out whether GU cross GV does that, or negative GU cross GV. In other words, GV cross GU. And we'll do some examples, and I hope it'll become clear how we do it there. But we need to figure out which one of those two is our positive unit normal. And in every one of these questions, we're going to tell you what direction we want the positive unit normal to point in, and we need to figure out which one of those points in that direction. Does that make sense? Similarly, if we have like a closed surface, say like a sphere, oh, beautiful, we can have outward pointing normals. So our normals would be pointing towards the outside of the sphere, or we could have inward pointing normals, in which case our normals would be pointing inside. And that's the way we usually do it for closed surfaces. But that is how we give our surface an orientation. We pick a normal vector at every point, and there are two options for unit normal. One pointing towards one side, one pointing towards the other side. But that's what it means to give your surface an orientation. Okay. Does that clear that up? Because that is sort of maybe the most important bit of all this. The bit that's different from what we did for integrating scalar functions. Okay, so the way we integrate vector functions, or vector fields, rather, is the same as for scalar functions. Let me write it like this. So if we parameterize our surface, actually, no, you know what? Let's do it like this. Okay. So the way we integrate a vector field is, of course, almost always we're going to have to parameterize a surface. So we're going to parameterize it as g of uv, where u and v lie in D. So either give bounds for u and v or give some region where u and v live. So that's step one, same as always. Step two is we use that parameterization. Let me say it like this. And this is really the only different step here. ds, d vector s, becomes that n of uv, not the unit normal, just either gu cross gv or gv cross gu. dA. So dA, there's du dv or dv du, depending on what the situation with d is. And so I want to emphasize here. I'll say in a second. And then we go to our function and replace x, y, and z. With their parameterizations in the vector field. And then we integrate over D. So we get f of g of uv, replace x, y, and z in your vector field with their parameterizations. We dot that with n of uv dA. And this is slightly different than what I did yesterday. I just said gu cross gv, but it could be the opposite Could be that, or could be negative of that, or. So it's going to be plus or minus that, depending on the orientation. But this is exactly the same as what we did for scalar functions, except there, for scalar functions, d capital S was magnitude GU cross GV dA. Now we're just taking away the magnitude, and we need to be mindful of the orientation. So if we take the magnitude, it doesn't matter whether we take plus or minus GU cross GV. We're going to get the same magnitude. Now we need to be mindful of the orientation. So I'm going to call it N of UV. And that's going to be either GU cross GV or negative GU cross GV, depending on the orientation. But I want to emphasize this is exactly the same process. Parameterize, replace X, Y, and Z with the parameterizations. D vector S becomes GU cross GV dA or negative GU cross GV dA, and then integrate over D. Okay, I spent longer on that than I wanted to. My apologies. Okay, so the easiest way to really understand what's going on is by doing several examples here. Okay. So let's calculate the integral over the surface S of the vector field F, where F is the vector field 0, 0, x. And here we're just going to parameterize S. So S is given by G of UV is U squared V U cubed minus V squared. Here, U and V are both going to lie between 0 and 1. Okay, not done yet, because we need to specify what the orientation on our surface is. So we say, in this problem, we say this has the upward orientation. Okay, so we have our surface, we have our vector field, and in fact, we're already parameterized. We're already given a parameterization of our surface. So that's nice. That's step one. Surface is already parameterized, so we can just jump ahead to calculating d vector S and then plugging everything in. Okay. So let's figure out what N of UV is. So we need to check, basically what we do for this is we either, as we'll see, memorize the form of N of UV, the cross product for certain things. It'll be very convenient to do that for certain, to memorize, because it cuts down a lot of the calculation you need to do. Or we need to calculate the cross product of GU cross GV and then see if that is the correct orientation. And if it's not, then we flip it. So let's do that. Okay, so we need to take the cross product of GU and GV. So GU, we do GU, we go component by component in the parameterization and take the derivative with respect to U. So the first component becomes 2U, V becomes 0, and the third becomes 3U squared. When we take the partial with respect to V, we get U squared becomes 0, V becomes 1, and then U cubed minus V squared becomes negative 2V. So then, we take the cross product of GU and GV. We do it in that order first, and then see if that gives us the right orientation. And if it doesn't, we know we need the opposite one, so we just flip the signs on everything. So taking the cross product, so we got 2U, 0, 3U squared, 0, 1, negative 2V. When we do this, we get negative 3U squared, 4UV, 2U. Okay, so does this give us the right orientation? If we look at this vector, is it pointing upward? In other words, to know whether we're pointing upward, we look at the z component. Is the z component so let me just say this, upwards means z component is positive. Well, lovely. Our z component here is 2u, and we know u lies between 0 and 1. And so it is indeed positive. The j component is multiplied by negative 1, yes. So it's negative, right. So it would be negative 4uv times negative 1. I sort of did that all without, yeah. I sort of blew through the work just because we know how to take cross products. And that's not the important thing here, yeah. Okay, and that is indeed the case here. Because 2u is positive. So this is the positive unit normal vector. This is going to be our n. Note, if, for instance, we got like negative 2u at the end, then this would not be our n of uv. Negative of this would be it. Does that make sense? But we take one of the cross products, see if that gives us the right orientation. And if it does, we take that to be our n. So this is going to be our n, what we're going to plug in to our integral because it gives us the right orientation. Does everyone understand that point? That's important. And I need to move on because we need to do more examples too. Okay, so that is our n. We have that. So now we plug everything in. So we integrate over d, where u and v live. Well, u goes from 0 to 1. V goes from 0 to 1. Our f with 0, 0, x but we need to replace x, y, and z with their parameterizations. And x in this case was u squared. So we get 0, 0, u squared. So that's our vector field, where we replace x, y, and z with the parameterizations. And then we dot that with the normal vector, or in, not the unit normal vector, but in, which we said was negative 3u squared for uv, and then 2u, 2u. And then our dA is just du dv. Right, dA depends on what the bounds on u and v are. And it's a rectangle, so it doesn't matter what order. So that's our uv.
Did we assume right, u was equal to x to get the u squared for the z component?
No, so in our parameterization, x, the first component is what x is. X is u squared. And then y would be the second component, which would be v, and then z would be u cubed minus v squared.
Okay, perfect. Thanks.
And so 0, 0, x becomes 0, 0, u squared. Okay, so we take this dot product and we integrate. And it just becomes a standard double integral. So we get 0 plus 0 plus 2u cubed du dv. And that's a very straightforward integral. We just get 1/2. The important bit, though, as always, is parameterizing our surface, which thankfully was done already for us, and giving it the correct orientation. And so that's doing the cross product and determining if that's the right orientation. Okay. Any questions about that one? Let's do a more difficult one. Yeah, so when we're given an orientation, basically we're always either, if it's a closed surface, we're told it's outward or inward. And then we need to figure that one out. Usually it's mostly spheres where we need to figure that one out, but sometimes they might ask us other things. And I'll tell you how to just memorize what to do with spheres. But for non-closed surfaces, we'll be told either like upward or downward. So in the positive z or negative z, or we'll be told with like the positive y or negative y orientation, or positive x or negative x orientation. So usually we're going to be told the sign of one of the components. And we'll see an example of that after the sphere one. God willing, we get to it. If not, then we'll do that on Wednesday. Okay. So that one was kind of free because they gave us the parameterization, but they usually don't. So let's calculate the flux of the vector field Zx1 across the upper hemisphere of the sphere, x squared plus y squared plus z squared equals 1. And here, since technically we're not dealing with the entire sphere, but consider the entire sphere, we're going to give that sphere the outward pointing orientation. And then we're just going to consider the upper half of that guy, but keep the unit normals pointing in the same direction. Okay, so spheres are common enough that you should just kind of have how to parameterize them on speed dial in your brain. And then just remember the form of the unit normal vector. So I already told you what the magnitude, sorry, not the unit normal vector. I already told you what the magnitude of g phi cross g theta looks like in this case, and you should have that memorized. Now I'm going to tell you what the vector form of that looks like, not taking the magnitude of it. But step one. Let's parameterize our surface. So we're calculating the integral of f over s. So first thing we need to do is we need to parameterize our sphere. Okay, so we're not getting the entire sphere, we're getting the upper hemisphere. So we're going to use spherical coordinates. And of course, we're going to replace rho with 1, because the sphere x squared plus y squared plus z squared equals 1 is the surface rho equals 1 in spherical coordinates. So we're going to be left with phi and theta. And x, instead of rho sine phi cos theta, is going to be, whoops, sorry, 1 sine phi cos theta. I'll just write that 1 in parentheses there. And then same, y is going to be 1 sine phi sine theta. Z is going to be 1 cos phi. So we just replaced rho with 1 in this case. And we also need to determine the bounds for rho and phi. Sorry, for phi and theta. So we get the upper hemisphere. So phi goes from what to what?
Zero to pi.
Close. So that would give
pi.
us the entire sphere. We just want the upper half. So it'd be 0 to. Sorry, did you say something after that?
Yeah, pi halves.
There you go. Yep. 0 to pi over 2. And then we go all the way around the z-axis. So theta goes from 0 to 2 pi. Okay. So this is our parameterization. Cool. Step 2, let's determine our normal vector. Okay, so I'm going to give you a shortcut that's going to save you a lot of time on these, and you should memorize this. So have this memorized. So for a sphere of radius capital R, centered at the origin, the outward pointing normal n of phi theta. So I'm using phi and theta instead of u and v here because phi and theta are what we're calling our parameters. Is going to be, this will be easy to remember. It's going to be similar to the magnitude one. It's going to be the radius squared sine phi. So that bit is the same. And then now we're multiplying that by what I'm calling E sub r, the radial unit vector. And let me tell you what that is. And it'll be easy to remember because it's basically in our parameterization. And that is basically going to be your parameterization minus, but turned into a unit vector. So it's just going to be sine phi cos theta sine phi sine theta cos phi. So if we look at our parameterization here, we have exactly that here. And if we had the sphere of radius r, we would be multiplying each component by r. So basically all we're doing is we're getting rid of the radius here. We're dividing by the radius. Our radius happens to be 1, so we get exactly the same thing as we got in the parameterization. So all you're doing is you're taking your parameterization, you're dividing by r. That's the radial unit vector. So we're multiplying that by r squared sine phi. And I think that's the easiest way to remember the outward pointing normal. Remember, this is the outward pointing normal. So any confusion on this point? You could calculate this if you like, but there is a lot of calculation and simplification that goes into this. So we're getting the radius squared, radius of your sphere squared, sine phi times sine phi cos theta, sine phi sine theta, cos phi. So basically you could multiply each component by the r squared sine phi if you like. I just like to pull it out, and I find it easier to remember that way. Okay, so that's the outward pointing normal. If we have the outward orientation, that is our guy. So in this case, our radius is 1. Oops. So we get our n of phi theta is just going to be the radius squared, which is just 1. Radius squared sine phi times sine phi cos theta, sine phi sine theta, cos phi. So this is just a vector function multiplied by, or a vector field multiplied by a scalar.
And then if the P, is that phi, sorry, or is that rho? Rho. Would there be like, if that could we, well, we got like the G of like sigma comma theta. If there, instead of 1, if phi wasn't 1 or whatever.
Yeah, so if the radius was say 3, then this guy is the radius squared, so this would just be 3 squared in that case.
Okay, and then what about like the vector in front of that? Like we have sine. Would that be like square root of 3 in there, sine of
No, so the only thing that changes between different spheres is this little bit here.
okay, so
This
that
is always the radius squared. This is the same for every single sphere. This is the radial unit vector.
okay,
It's the unit
cool.
vector pointing in the direction of.
All right. Thank you.
Yeah. Okay. All right. So that's our normal vector, and let's put it all together. Let me write this down. So we want the flux across the surface. And so we know, okay, so phi goes from 0 to pi over 2, we determined. Theta goes from 0 to 2 pi. Our vector field F was Zx1. We need to replace x, y, and z with their parameterizations. So z is cos phi in our parameterization. X is sine phi cos theta. And 1 is 1, of course. And we said our unit normal vector now I'm just going to bring this 1 squared sine phi inside the vector, just so I'm dotting 2 vectors and it's a little cleaner. So I'm multiplying each component by radius squared sine phi, which is just sine phi in this case. So we get sine phi cos theta times sine phi, which is sine squared phi cos theta, sine squared phi sine theta. Sorry for the messiness here. And then the last component is sine phi cos phi. So that's d phi d theta. So let's dot this together. Okay, so we get cos phi times sine squared phi cos theta. So that is, we can just write it like that, that's fine. Cos phi times sine squared phi cos theta plus, next component we multiply together, sine phi cos theta times sine squared phi sine theta. So we get sine cubed phi sine theta cos theta plus 1 times sine phi cos phi. D phi d theta. Okay, so we could spend a while doing this, or we could be 5-head about it and notice that, okay, so when we integrate with respect to theta, we have this bit here, cos theta. When we integrate that from 0 to 2 pi, that's going to be 0. That's just sine theta. And then sine theta cos theta, we could use sub, and we end up getting 1/2 sine squared theta. When we evaluate that at 0 and 2 pi, also going to integrate to 0. So when we integrate both of these terms with respect to theta, we get 0. Wouldn't expect you to see that on an exam, but it's good to be on the lookout for that kind of thing. Even though we don't integrate with respect to theta first, it doesn't matter because that's the term that affects it when we do integrate with respect to theta. Okay, so then we're just left with sine theta, or sine phi cos phi. So sine phi cos phi, we can use sub. That becomes 1/2 sine squared phi. We're integrating from 0 to pi over 2. And so that just becomes 1/2. And so in the end, we just get pi. There's nothing too fancy that we did there. I just skipped over a lot of steps that you all could have done yourselves, but that's not the important thing. Important thing is getting that integral set up, knowing how to parameterize a sphere. You need to know how to do that, sphere of radius r, and knowing the outward pointing normal. That is a very good thing to have memorized, and I absolutely would suggest you have that memorized. So that was the radius squared sine phi times the radial unit vector. So basically your parameterization is the radial unit vector, where you forget about the r everywhere. Then you replace x, y, z with the parameterizations in the vector field, dot it with the normal vector, and then integrate over d, where phi and theta live. Okay. Any questions about that? I'll summarize. We'll do one more example where we do a integral over of a vector field over the graph of a function, and we'll see the shortcuts for that tomorrow. And then I'll kind of summarize all the shortcuts you should have memorized for surfaces tomorrow when we do that. But any other questions? Okay, if not, I'll head over to office hours and have a good one. I'll see you guys on Wednesday. Later.